All right, hello everybody. So we're going to finish up section 6.3. We're going to talk about section 5.1 and then also introduce the main concept in section 6.1. This section 6.3, we introduced matrices and we talked about adding and subtracting them and also multiplying them. Here's one very tiny glimpse as to how matrices can be used. So we've got a irregular polygon right here, and I can identify the vertices, these four corners. Well, those four corners are just composed of x's and y's, so I can organize them into a matrix where all the x's are in the top row, all the y's are in the bottom row. It really doesn't matter. I could put the x's in the bottom row. I just have to be consistent. I want to be organized, so I want all the x's in one particular row and all the y's in one particular row. Well, another matrix I can add to that would be this, just randomly. So this matrix, remember all the x's were in the top row, so I'm adding -2 to really all the x's on the corners, and I'm adding nothing to the y's. So when you think about these ordered pairs, all these ordered pairs are going to shift suddenly, very quickly, just by adding this one matrix. So just by adding -2 to all the x values and adding nothing to all the y values, I mean, mathematically, we get this. I'm sure we can do this. This is just a matter of adding integers. But how does that change the actual shape of this polygon? Well, I've got these new vertices. One is -4, 1, which is right here. The second one is 2, 4, so I go all the way to 2, 4. And then I go to 4, 0. And then I go to 2, 1. And to connect it, I go back to my original vertex. And as you can see, it shifted that piece to the left 2 units. And so to extrapolate this a millionfold, and this is how, at least this is how it used to be, the video games and cartoons used to work. You could draw a character, and let's say you've got the polygon character, this really boring polygon shape, and you put in the computer the coordinates of all the vertices. And if you want that character to jump 2 spaces to the left, like let's say there's a B over here and he wants to avoid it, so we need to move him 2 spaces to the left, we just add this matrix and so to the computer. So the computer will change the image 2 spots to the left, and if you do that quick enough, it just looks like they kind of jumped 2 spaces to the left. But a lot of matrices would be involved. You could add several matrices to make the character kind of elevate a little bit and then land. You can make it run, etc. So just by all these, they're all just transformations. Another transformation is this. What does this do? If I can't add that to this matrix because it's not the same order. Remember, this is a 2 by 4. So if I want to add or subtract anything, this has to be a 2 by 4. But I can multiply this. Can you think what will happen if I multiply that? You remember you multiply the row by the column. So this row, -1, 0, is going to be multiplied by this column, this column, this column, this column. The second number is 0. So when I multiply the second number in this column, I'm multiplying all the y's by 0. So the y's won't change, but the x's will become their opposites. And the bottom row, 0, 1, when I multiply all those columns, 0 times all the x values, well, nothing will change, and the y values will stay the same. So when I multiply those, what is the result? So if you were following along there, you were taking the opposite of all the x values. So 2, now I've got 2, 1, which is right here. And then I've got -4, 4. And then I've got -6, 0. And then I've got -4, 1. And then you connect the dots again. And there was a reflection over the y-axis, which is the result of multiplying all the x values by -1. And there's just 100 more we could do, but I hope you get the idea that you could take a shape and transform it by either adding or multiplying a matrix. Now, going back to section 5.1, which we skipped over chapter 5 completely, we'll get back to it in pieces. And here's the first piece: solving systems of equations. And a system of equations is at least two equations that are thought about at the same time. So two equations that are considered at the same time. And the solution is what they have in common. Oftentimes it's an ordered pair, but it doesn't have to be. I can have three variables, and then it would be an ordered triple. Or I can have four variables, and it would be an ordered quartet. I don't know what you would call that. But so for these two examples, they're just two variables. So the only solution is an ordered pair that they have in common. Negative 1, 7 is the solution to this. Because if I plug in negative 1 for x and 7 for y, this will become negative 17. This will become positive 40. So the ordered pair has to satisfy both equations. Now this one over here, you got a parabola and a line. There are two solutions. There are precisely two ordered pairs that satisfy both the parabola, that are on the parabola, and on the line. Graphically, graph should really be your best friend, because the graph tells you answers so very quickly. If you were to graph both of these lines, the green line has many, many ordered pairs, so does the purple line, but they only have one ordered pair in common, this ordered pair, and this is negative 1, 7. Here, this parabola has many, many ordered pairs, so does the line, and they have precisely two ordered pairs in common. One is 0, 2, the other one is negative 3, 11. And there are a few ways to solve these. One is by graphing. You just graph the two equations and see where they intersect. Another way is by elimination. So you can either add or subtract equations. Let's take a look at this example. So this company makes canoes and they sell canoes. Well, you can't make a canoe for nothing. They have a fixed cost of $18,000. So no matter what happens, they're spending $18,000. That's probably on supplies and labor and rent. So no, even if they make 0 canoes, they're going to spend $18,000. Plus, it costs them $20 to make a single canoe. So their entire cost can be organized by this: $18,000 no matter what, plus $20 per canoe. And I can write that as a function if I let x equal the amount of canoes that they make. And the cost would be a function of x. Now, they sell canoes for $80. Well, that's just all the money that they take in just is totally based on how many canoes they sell. So 80 times the canoe, the revenue is again based on x, where x is the amount of canoes sold. Well, this is a system. I've got two equations and two variables. I can think of cost and revenue. They're both in terms of money, right? So I'll just call them y. Y equals 20x plus 18,000. Y equals 80x. And now I can solve this by elimination. And I could subtract. I could subtract these two equations. And what is the result of that? They call this elimination because if I happen to subtract in this instance, y minus y will get eliminated. It is 0. Don't forget the equal sign. And then 20x minus 80x is negative 60x. And then 18,000 minus nothing is still 18,000. And now you've got one equation and one variable. So now there's a lot of hope that we can solve it. And you're 2 steps away, right? Subtract 18,000, divide by negative 60, you get 300. But what does that mean? X equals 300. Remember, X represented how many canoes that they made and sold. So X equals 300 is the magic number that it'll give you a particular cost and it'll give you a particular revenue, but it'll be the same. It'll be the same. When this company makes and sells 300 canoes, all the money that it costs them to make that amount, plus all the money that they get from selling that amount, will be the same. So that's like their magic number. That's their break-even point. So if the company makes 300 canoes, week in and week out, they're not really making any profit. They're just barely surviving. So they want to make at least 300 so they can make more money. You can also eliminate things by addition. Now, right here, adding won't eliminate anything. If I add, I get 7x. And if I add these two, I get 7y, or negative 7y. So nothing got eliminated. The key is to eliminate a variable. Here, this one was a little bit easier. I can subtract, and the y's go to 0. But we are allowed to we have a lot of freedom with these equal signs. I can multiply anything I want, and I choose to multiply by something so that I get either the x's to be opposites or the y's to be opposites. And I'll multiply this top one by positive 5. That will make this 10x. And I'll multiply the bottom row by negative 2. That'll make this negative 10x. And you have to multiply everything by 5 and everything by negative 2, giving us this new system. This system is the same thing as this first system. It looks different, but it's precisely the same thing. Because if I multiply both sides by 5, it doesn't change the solution, because I kept the balance. Multiply the left side by 5 and the right side by 5. But now I've got a big advantage. I can add these two equations. And 10 plus negative 10, that will eliminate. That equals 0. The y's don't cancel out, but that's okay. It becomes 35y. If I add these, I get negative 140. Divide by 35, I get y equals negative 4. But remember, the solution to a system is the ordered pair that satisfies both of these, both equations. I just know the y. I need to know the x too. So to find the x, you take negative 4, and you plug it into any equation that has an x and a y. You got 4 choices. You can plug it into here, this third one, or this fourth equation. Any one of those 4 will do. I just chose the first one. Replaced y with negative 4, solve for x, and I get negative 2. So the solution to the system is negative 2, negative 4. Finally, last thing for section 5.1 is solve by substitution. So I have the last 15 years, I've not paid a single penny for a landline phone. I grew up with a landline phone, but the amount of landline phones in this country is definitely decreasing. They're all being replaced by cell phones. And in fact, I'm not sure I know anybody. My parents have a landline phone. I don't know anybody else. But this equation represents the amount of landline customers in millions based on X years after 2000. So Y would be the amount of customers in millions. X is the amount of years after 2000. And this equation represents a similar model, but for cell phones. So that's a system. And what happens if I solve this system? What happens if I find the ordered pair that satisfies the landline situation and the cell phone situation? Well, let's solve this by substitution. Notice that y equals this. Y is solved for. So every time in this problem I see a y, I can replace it with 19.8x plus 98 because they are the same thing. Replace means substitute. So I could substitute y with this. And so now I'm going to rewrite this top equation, but instead of writing y, I'm going to write this. And then I solve for x. I discovered that x is 4.14. That caused me a little bit concern. I had to think about, what was x again? X is the years after 2000. So this is a little bit after New Year's Day in 2004. So a little bit after 2004, January, February. But that's the x value. To find y, you plug x into any equation. You only have 2 options really here. So the y value is that. Y represented the amount of customers in millions. So in the year 2004, there were, let me reveal the solution here. Here's the mathematical solution. What does that mean? That means in a little bit after the year 2004, there were about 180 million landline customers in America and about 180 million cell phone customers in America. But the amount of cell phone customers are increasing. So look at this slope. This is a positive slope. this first equation has a negative slope. If you were to solve for y, the slope would be negative 4.3. So the landline equations are decreasing as time moves on. Cell phone customers are increasing, and they happen to be the same in the year 2004. Okay, that was section 5.1. Just a one page on section 6.1, matrix solutions. All these systems, not many of these systems can be solved by using a matrix. And I believe it's only actually for linear systems, but that's what we're going to be studying. So here is another system, and just take my word for it. The answer is 2, -3. When x is 2 and y is -3, then this 5x plus 7y will equal -11, and this will equal 18. Out of all the ordered pairs that both of these lines have, the only ordered pair they have in common is 2, -3. And we could solve this by elimination, by graphing, etc. But we can use a matrix to solve it. And what we do is we convert, and this is the heart of this next test, is to use matrices, is to convert that system to what's called an augmented matrix. So you have, imagine a line there, that I just drew, and this system can be converted to this matrix. So do you see the similarities here? The first row is 5, 7, -11. So you're ignoring not only the variables, but you're also ignoring the operation. You don't see a plus sign there, right? And you don't see an equal sign either. So it's just the numbers, just the coefficients. And then the second row, same story. And think about it as this is like the x column. It has to be organized when you put it into a matrix. All the x's have to be lined up in one column. All the y's have to be lined up. It doesn't matter where you put them, but they just have to be lined up. And then it equals the constants. So the two constants have to be in the same column, and then the equal signs have to be lined up. Then you put it in this augmented matrix. How does that help you? Well, remember the solution was 2, -3. So we can go to our calculator for the Inspire people. Okay, so for the 84, Amelia, if I'll show you how to do this on here if you stick around. But for the Inspire people, you want to type in RREF. I'm not sure if that's the fastest way. Let's go to menu and matrix, and we want reduced row echelon form. That's what we want. And it's waiting for a matrix. So we need to tell it what matrix. So I go to this button, remember? And this matrix had 2 rows and 3 columns. And now it's waiting for, what were the coefficients? And I forget already. They were 5, 7, -11. And then 3, -4, 18, I think. Let me double check. Yep. Okay. This gives me this. But what does that mean? Remember the answer was 2, -3? There's your answer. But if you really want to feel good about this, I really want you to know, what does this mean? There are 6 numbers here. How do I know that the answer is 2, -3? This is how you interpret this matrix. Remember, you can think of this augmented matrix as 5x plus 7y equals -11. And this is 3x minus 4y equals 18. So you can imagine in your head putting in x's and y's and an equal sign and things like that. Well, with this, do the same thing. This is 1x plus 0y's equals 2. So in other words, 1x plus 0y's equals 2. In other words, x equals 2. And here, 0x's plus 1y equals -3. So no x's, but 1y equals -3. So y equals -3. So that's a fantastic way to solve these things. It makes section 5.1 almost obsolete if you have a calculator. But we're going to do more with this. But I want you to know that you can always RREF it. RREF it. RREF, put the matrix in, press enter, and you're going to get your answer right away. And that's what we're going to be studying. That's it for today. If you want to know how to do this on the 84, I'm going to do that right now. Otherwise, I'll see you for the test tomorrow. So for the 84, unfortunately, it's more complicated. You have to create the matrix first. And there's matrix right here. So I press second matrix, and I need to, here are all the names of the matrices. And math, those are all the operations I can do. Edit, I need to go to edit first to create a matrix. And it first wants to know the order. Well, there are 2 rows, and hold on a second. And there are, come on, 3 columns. And I type it in 5, enter, 7, enter, -11, enter, 3, enter, -4, enter, and then 18, enter. All right. And then quit. So once you've done that, now in this calculator's brain, it has this matrix. So now we need to RREF it, reduced row echelon form. So we go back to the matrix menu and see now name A. There's a matrix here waiting for me, but I want to go to math and find reduced row echelon form. And there it is, RREF. Press enter. Now the calculator is waiting. What does it want? Which matrix does it want to take the reduced row echelon form of? And we want matrix A. So again, we go back to the matrix menu, and our cursor defaults to the first one. So we just make sure your cursor is on the one that you want. You press enter, and you press enter again. And finally, it gives you the reduced row echelon form of this matrix. So we interpret that as 1x equals 2, 1y equals -3. So the solution is 2, -3.